But maybe maybe the screen is not full screen, correct?
Yes, true.
Yeah, but I don't know how can I fix it, in fact, because my screen here, it's this ultra wide screen. So so how can I don't know.
Screen now.
Yeah, you can see the screen, but it's much better, right?
Yes.
Yeah, it's bigger, but the slides are still like shown to the left, but it's okay. I think now it's working.
I don't know how to share the application itself instead of sharing. So this one here, we should share application, correct? I have another screen here, but unfortunately, it's not working today for some reason. So anyway, because I won't make it. Okay, maybe it's no signal. So strange because I don't have a signal. Okay, so maybe after the break we can try to fix it one more time, but we can start now. So multi-class classification. In multi-class classification, in fact, the idea here is to try to build a model, one model for each class. So here we have number of classes, right? And we need to build one model for each class. We did it last time with 3 classes, and from those 3 classes we got 3 models, as you can see here. So I mean, it's a binary classification problem. I mean, we have 2 features, x1 and x2. We have 3 classes, but we will have a classifier, logistic regression model, which will deal with each class as one class, and the rest will be the rest. We call it one versus rest strategy or approach. So in this case here, for example, for the green one here, we deal with it as a class, and the rest will be just the rest. So it will be converted into binary classification problem. For the red one, of course, we will do the same. We will try to find a decision line using this model to classify the red class as one and the rest as the rest. So we call it OVR, or one versus rest. We had here just last time, we plotting the data, loading the data. We just need here to, where is the model? So when you select logistic regression, you can specify, in fact, do you see here? So you can specify that it's multi-classification. So in this case, for sure, you will get better results. So I did this make PLUPS one more time, but in this time using 4 classes. So I just generated 4 classes, and here standard deviation will be 1.2. So in this case, you can select. I mean, those make PLUP data sets. It's a toy data sets, in fact, or artificial data sets. You can generate any data set with some specification to test your algorithm. So here, for example, I just selected 4 clusters or 4 centers with standard deviation 1.2. So finally, we have 4 classes, right? So you can control the overlap.
Excuse me?
Yes.
Could you please increase the size of the slide? It's like very little. It's so difficult to see. Yeah.
Okay. So we will stop and try to fix it. Because I have a problem here. I have one screen which cannot connect to the computer. So maybe I can. Okay. So I will disconnect this big screen. I will go back to my. Now it should be better, right?
Yes, now it's better.
Okay. Because I'm just disconnected. I'm disconnecting my screen.
Yeah. This is visible. We don't need magnifying glass for this.
Okay, but I have a problem here. In fact, we got a device, but it's not working today for unknown reason. So anyway, I can try to. I will try to restart it one more time. Oh, it's still not working. Okay, so it should display. I mean, I should have my PowerPoint here, so it will be easy to write and annotate. But unfortunately, it's not working today. So anyway, we can start only using my screen here, my computer screen. Yeah. So as I told,
sorry, if possible, which slides are these? Like slide
number 12. It's from last week. It's a slide
from last week. Okay, thanks.
Yes. So it's I mean lecture 4. So we just need to revisit some slides. So I just I want to mention that this one, you need to use this multi-class. So we need to use OVR here. You can do it without or with it. So when you are doing it with this multi-class option, you for sure you will get better results. So I just repeated it for one more example. In this example, I selected 4 clusters, and you can select standard deviation. By the standard deviation, you can control how much overlap between classes. So you can make it really very challenging for your model. And we just used this strategy, which is one versus the rest. You can say that a perceptron, when we have binary classification problem, it's one versus the other, or one versus one, for example. But here it's one versus rest. One versus rest, we deal with each cluster as one and the rest as the rest of the data set. So you can just convert it into binary classification. And in this case, we will select, or we will build 4 models, 4 perceptrons, for example, one for each cluster. So and finally, we can generate those 4 lines, the decision lines. This line, for example, it will differentiate or separate red class from the rest. The green one, the green line will separate the green one from the rest. The blue one will separate this one from the rest, and so on. So this strategy, we call it one versus rest. So
yeah.
if you have a problem which is not very challenging, in fact, because at the end you will generate a line, but also you can control it, in fact. So you can use high order feature, and then when you select high order feature, you can find really very complex decision boundary. But simply here we have 2 features, x1 and x2, and using this one versus rest strategy or approach, for example, we can generate a decision line to separate each class from the rest. So we will have this one which will separate the red class from the rest. The green one will separate the green class from the rest, and so on. So in this case, we will have 4 models or 4 perceptrons, for example, or regression models, binary regression, linear regression model. And at the end, each model has 2 inputs and 1 bias. So we will have omega 1, omega 2, and p, omega 1 and omega 2 and p. So we will have 1 model for each class. Yes. Do you have any question in that part?
Yes, you said that we use the standard deviation to control the overlap between the classes. Can you elaborate on these points?
Yes, I mean this one because I mean each data set, it's 2 data set, in fact, or artificial data sets, and it's in Python or in sklearn. And the idea behind it is to try to because data collection, sometimes it's a problem. So sometimes it's hard to have a specific or a data set with a special requirement or specification. So there are lots of data sets, in fact, generators in Python. You can use it for generating a specific data set for testing your model. So this one here, it has lots of options. So if you just Google make PLUPS, you will find all options. But here, for example, I just selected how many centers of clusters. So if you want to generate 4 clusters, so it will generate first 4 centers by random, right? And after that, it will generate a number of points. It's 100 points, in fact. I mean, by default, it should be 100 points, but you can also select, you can choose how many points you want to generate. And this 1.2, it's a standard deviation from the center. So you need to know how the distribution will look like around each center of each cluster. So if you increase this one, it means that there will be some overlap between those clusters. So I mean, we will get some overlap here. So if 1.2 from the center, if it's 1.5, for example, 2.5, you will see some overlap between those clusters. So it's just the overlap, and when we have overlap, it will be more challenging, right? Now it's very simple because we have clear distance between each cluster. But if you increase the standard deviation, there will be some overlap between those clusters. So it will be more challenging for the model. Now we can just use linear regression model, which will generate a straight line. So we will have a straight line, and it will be very enough to classify those classes. But if we have really complex overlap, in this case, it will be impossible to use. I mean, we can use a straight line, but of course we will have low performance. But you can, I mean, there are many ways to, I mean, to turn around this, I mean, restriction. But this 1.2, it's a cluster standard deviation. So how the data will be distributed around the center point of each cluster. So you can use this one, for example, for testing and supervised learning, because it's centers and it's very ideal for k-means clustering, for example, right? So at the end, I did it for Iris. We did that also for Iris dataset. As I remember, we selected 2 inputs. Today we will talk about feature selection. So if we have to select 2 from 4, we know Iris dataset, it has 4 inputs, but if we need to select 2, which 2 should we select? So we will study today also an algorithm for feature selection. So which 2 should we start with? For example, if we really have restrictions on, or if I need to reduce the number of features, which 2 should we select? So this Iris dataset, we have 4 features: sepal length, sepal width, petal length, and petal width. And it has 3 classes: Setosa, Versicolor, and Virginica. So if you want to use one versus rest, how can we do it? We have 3 classes. If you will select 2 inputs or 4 inputs, we don't care. In fact, I just selected 2 inputs because we want to plot it in 2-dimensional space, right? So each perceptron will have omega 1, omega 2, and bias, right? So it will be similar. We have omega 1, omega 2, and bias. So I just repeated this one for Iris dataset, and this is the code, and this is how the decision how it will look like. So I did it for training. I divided the data into training and testing. So for example, we have here divided the dataset, Iris dataset, into part for training and part for testing. I used this train test split. So this function is very important from sklearn. So from sklearn model selection, you need to use train test split. Train test split, it will divide my dataset into 2 sections, one for training and one for testing. And we have here test size. You can select test size or train size, in fact. So I'm choosing here test size equal 0.3, which means the training size will be 0.7, which means 70% of the data will be used for training and 30% will be used for testing. And remember, we have here this issue, this option, stratify. I mean, stratify equal y. So in this case, it will generate, balanced data set. So all clusters are equally represented. So when we use stratify here equal y, so do you see how many? Because we have 3 clusters, we have 50 points for each cluster. In fact, because the total size of my data set it's 150 points. So we have 50 plus 1, 50 plus 2, 50 plus 3. So when we use the stratify here, we will be sure that we will get equal number of clusters in each set. So in the training data set, we will have 35 from class 1, 35 from class 2, 35 from class 3. In the testing data set, it will be 15 from class 1, 15 from class 2, 15 from class 3. So this option here, it's very, very important because it will help us to get, balanced data set as much as possible. Because imagine that you have class 1, 50, class 2, 45, class 3, 35. So it will be impossible, right? It will be within each class. So, it will be equal within each class. So I just did it and I tried to plot the decision line. In plotting the decision line, as we mentioned last time, there are many ways for doing it. So for example, you can generate this grid, right? Unfortunately, I cannot write today. So we can just, we can have this grid, for example. I'm plotting because this one is disconnected, in fact. So this is a problem because I cannot see it. So you can just generate a grid and you can find values. You can find the range of values for x1 and x2, generate a grid and apply the regression model, right? Model.predict at each point of the grid. So in this case, we can generate, and of course, each point, because the decision line at the end, it's a line, right? Or a plane, for example. So we will find the decision at its point of the grid, and we will plot this nice graph. So if you want to make it like this, it's possible. You just need to use this model.predict. Last time we did it several times by just finding the line, right? We have a line because we are plotting it in 2-dimensional space. So if I have x1, I can get x2 using those weight values, because the decision line it's omega 1 x1 plus omega 2 x2 plus p equals 0. So if I know x1, I can find x2, and we can plot it in 2-dimensional space. We talk about logistic regression and why logistic regression is important. It's a very popular algorithm in industry and so on. So we did that last time, and indeed also, indeed it's in this session it's a linear regression model, but we apply this activation function, Gaussian activation function, and we mentioned why it's useful. And finally, we have this linearly inseparable data sets. Some data sets are linearly separable. This one also, it's generated by Python, in fact. So this data set, it's generated, it's a customized data set, which can be generated from Python. You have two classes here, one class and one class and 0 classes. So it's binary classification problem. So we have features x1 and x2. We have two classes. Red class, it's 1, and the blue class, it's 0. So we have two classes. And we need to know how can we solve this problem, because it's inseparable, linearly inseparable. When it's linearly inseparable, it means we cannot find a straight line which can divide those two classes into two separate classes. So one way for solving it, for example, is to try to add high order feature. So this data set, for example, we have x1 and x2. So maybe we need to just add another feature, which is x3, and we can select x3 equal x1 square and plus x2 square, right? So you can select, or just you can just choose x1 square, replace it the two features with x1 square and x2 square. In this case, you can get a curve, or you can get a circle. In fact, the decision line will be a circle. So adding a new dimension can make your problem much easier. So for example, here, this plot, it's in two-dimensional space, and if you look into it, it's inseparable. When we look into the two-dimensional space, it's inseparable. It's impossible to find a decision line which is function of x1 and x2, which can separate the data set into two separate classes. But if we can use, for example, x1, x2, and x3, for example, where x3 equal x1 square and x2 square, if you can plot it into three-dimensional space, in this case, it looks like separable, right? So in this case, we can just generate a plane, and this plane will be used for classifying it. So finally, I used a logistic regression model using x1, x2, and x3, where x3 equal x1 square plus x2 square, and we can generate this plane. So this one can be used now for generating. Remember, I mean, logistic regression, it's like a perceptron. So it's just one unit. It's one neuron with some number of inputs and Gaussian activation function. So it's a very simple one, and we can use this simple. Okay, you can use a perceptron, right? You can use a perceptron with hard limb function for also solving this problem. But in this case, you must introduce a new feature, and this new feature, it should be a combination of the other features. How can we select it? This is the complex part. So I mean, this problem, because we can plot it, we can find out that, okay, x3 should be x1 square plus x2 square, because this one will be a matrix, will be a circle. So it will help us to find a decision line. So I just solved this problem. And I mean, I don't remember this iris classification problem. Yeah. But also, and we'll talk about, I mean, confusion matrix. Did we talk about confusion matrix last time? I mean, the confusion matrix, it's a table which is used for, I mean, describing the performance. So I'm using a small screen now. So, okay. Do you want to say something? Okay. So the confusion matrix, it's a way for just describing the performance of any classifier. So when you are building a classifier, for example, it's very important to plot or to display, calculate the confusion matrix and try to, I mean, in your result part. So if you are writing a paper, for example, so it's very important to get the confusion of your classifier. So the confusion matrix, it's, I mean, it's a very simple one. We have actual classes and we have predicted classes, and we need to know how many of the classes are correctly classified and how many are, wrongly classified, right? So we have two diagonal. In this diagonal, for example, the true positive and the true negative, this is the one which we need to maximize. And in the true positive, it's a number of positive classes which has been classified as positive. True negative, it's a number of negative classes which has been classified as negative, right? This one here, it's false positive. False positive means it's a negative, but it's classified as positive. So in this case, we can say it's false positive because it's originally negative, but it's wrongly classified as positive. And the false negative, it's positive, but it's misclassified as negative. So we call this one type 1 error and the type 2 error. And type 1 error and type 2 errors are very important. If you are building a system for a hospital, for example, or medical domain, it's important to find the type 1 error and the type 2 error because those two numbers are very important. Imagine you have a patient and this patient has coronavirus, for example, and you made a test for him. So some of those patients, they are positive and they are correctly classified as positive. So this one is okay. Some of them are negative and they are correctly classified as negative. So in this case, we need to maximize the true positive and the true negative. Because the accuracy, do you see the accuracy here? It will be true positive plus true negative divided by the total number of cases. So true positive plus true negative divided by true positive, true negative, false positive, false negative. So this is the accuracy. So the accuracy, it's the number of correctly classified cases, for example. So it is a true positive plus true negative divided by all number of cases. So we need to maximize this one. So when this one, it's 95%. When this one is 98%, we need to increase it. So if you want to increase it, you need to increase all numbers across this diagonal, right? And if you want to increase numbers across this diagonal, it means we need to decrease the numbers across the other diagonal, correct? So in the opposite diagonal, we have false negative and false positive. What does it mean, false positive? False positive, you have a patient who is negative corona. He does not have corona, but he has been classified as positive. So this one is okay. Maybe it will harm him a little bit, and it will. We ask him to stay at home for 2 weeks, for example, but it will not harm anyone because he is negative. But our system, wrongly classified him as positive. So we call it wrong positive, right? It has consequences. For example, maybe he was supposed to travel, for example, and he cannot travel now because he has been classified as positive. So he is false positive. But maybe also he will feel some depression because he needs to stay at home. He will feel depression because he doesn't have corona, but he feels that he is positive, right? But but originally he is negative, right? So maybe he will stay at home. He will take some medication. We will not allow him to travel. We will not allow him to go to school, for example, or to go to work, for example, for some time. So, but it will not harm anyone, right? It will not harm anyone. He will take some medications, some vitamins, but it's not a problem at all, correct? So type 1 error, it's okay. We can survive with type 1 error, but the one which is killing really, it's a type 2 error. Type 2 error, he is positive, but he is misclassified as negative. So he has corona, but when he did the test, for example, we just told him, no, you are negative. You are negative. So he will go to on board flying. He will go to work. He will go to office. He will go to school. Right? He is corona, but we will not give him any medication because we told him he is negative. So do you know how much problem, how much troubles we can make from this type 2 error? So type 2 error is really very complex and it's very tough. And those numbers are very important. So when you are building, if you are writing a paper, for example, and you are building a system for medical image classifications, for diagnosis, for example, those numbers for people from the medical domain, those numbers are very, very important. Type 1 error and type 2 error. So it's not only the accuracy, in fact, not only the accuracy, but also type 1 error. You need to display those numbers and discuss those numbers. Type 1 error and type 2 error. We need to minimize type 1 error and type 2 error. We have precision. Precision, it's the total positive divided by total positive plus false positive. True positive and false positive. So we call it precision. We have sensitivity. Sensitivity, it's a true positive divided by true positive and false negative. So those numbers are very important. And we have also, we have a tool in Python in sklearn for calculating those numbers. True positive rate, false positive rate, precision, and recall. Yes. So this is an example, and in this example, it's a binary classification problem for medical testing to determine if a patient has a certain disease or not. For example, it's a tumor diagnosis, for example. And in this case, we have two possible cases or two possible classes. It's yes and no, right? So it's yes and no. So you have maybe blood analysis. You have MRI scan, for example. You have lots of data, and you are feeding those data to your model, and this the model should just say yes and no, for example. So we have 165 in total, and the actual no, it's 60, actual negative, it's 60, and actual positive, it's 105. And for our model, so the model can predict 55 as positive and 110 as negative. So from this one, we can find true, positive, true, negative, right? So this one, it's a true, true, negative, right? This one, true, negative. This one, true, positive, correct? True, negative, true, positive. This one, it's false, negative, false, positive. So from those numbers, we can judge the accuracy of our model, and we can find the type 1 error and the type 2 error, and yes. For iris dataset, I mean, we have this nice we have this function in sklearn. I mean, if you want to do it in sklearn. So unfortunately, it's not here. Okay, but it's in the example. So if you will go to the example, we can find it. So in fact, if you want to calculate the confusion matrix, for any model, you just need to export confusion matrix from sklearn.metrics. So from sklearn.metrics, you need to import confusion matrix. So the confusion matrix will be used for, calculating all those numbers. So okay. Today I have a problem in my computer. We need to fix this. Yes. Sorry. So this one, we will calculate the confusion matrix, and after that we will plot the confusion matrix. So I did it for iris dataset, which we just finished. And for this iris, the accuracy was almost it's almost 100%. So this one will be true, negative, right? True, positive. This one, it's false, negative. This one, false, positive. So you have this logistic regression implementation. Logistic regression implementation, I just implemented it by myself. And I try to calculate the confusion matrix for the model. So we have this command here, you see? So you have this command, it's called the confusion matrix. And the input to this one, it's the actual classes, and the predicted classes. So we have y and y predict to calculate the confusion matrix. And this one for just plotting it. So how can we get the confusion matrix? You can import it from sklearn.metrics. You can import it from sklearn.metrics, and you can calculate confusion matrix. You can calculate also recall, precision. It has all those numbers. You can get those numbers in just one line. So far we have been talking about this single layer neural network, and in this single layer neural network we have only one unit, one perceptron, and this perceptron, it has number of inputs. We have an activation function. Maybe we have at the end, if it is adaptive linear unit, we have this one for unit step function. This unit step function, it's for just making decisions. So we will calculate net equal omega x plus bias, right? Omega x. And after that, we will apply it to the activation function, and the output from the activation function, we will use it because the number here will be a number between 0 and 1. So the output from the regression model, from the Gaussian function, it will be probability. In fact, it will be a number between 0 and 1, and we need to have a hypothesis because we need to classify it into yes and no, for example. So in this case, we need to use unit step function here, or a threshold function here. So for example, values greater than or equal 0.5 will be classified as 1, otherwise it will be 0. So if it is adaptive linear unit or logistic regression classifier. So this is the logistic regression classifier. It's the same as a perceptron. In the perceptron, this part will be the same. This part all time will be the same, even in neural network. This part will be the same. We will calculate summation of weighted sum of inputs. So it will be omega 0 times 1 plus omega 1 times omega x1 plus omega 2 times x2 and so on. We call it net. And after that, we will apply this value to the activation function. From the activation function, we will have a probability. We need to have a hypothesis here. So maybe the hypothesis, all probabilities greater than 0.5, it will be classified as 1, otherwise it will be classified as 0. So this one is used for binary classification. We need to remember this binary classification. If you have multi-class classification problem, so in this case we need to use several models from this one. This one versus rest. One versus rest. It's mean we are creating one for each class. So this one, it will deal with one class as 1 and the rest as 0, right? Do you remember the problem where we used this make blobs? Make blobs, we generate one for the red class, one for the blue, one for magenta, and so on. How this one work? We just generate a model for each class, and it will deal with this class as 1 and the rest as 0. And we call it one versus rest. This one, we have a cost function. So the cost function, it's this, summation of squared error. And the error, it's the difference between the actual class and the predicted one, correct? And it's a convex error function. And we update the weights, omega equal omega plus delta omega. So the task here, how can we calculate delta omega? We just use gradient descent. So it will be minus constant multiplied by partial by the gradient. So it's minus learning rate multiplied by the gradient. So it's minus eta multiplied by partial j by partial omega. So the idea is to find the partial j by partial omega. Partial j, this one, y, it's constant. So partial j by partial omega, so it will be 2 times half y minus phi, correct? Multiplied by partial y, it's 0. Partial minus phi, we will have minus again, minus times minus, minus times negative times negative, it will be plus, correct? And partial phi by partial omega, it will be x, correct? Because phi here, or net, it's omega times x, right? The output here, it's just omega times x, right? Yeah, if it is linear regression model, if it is a linear regression model, if it is Gaussian, it will be something else. Yeah, it will be y times y minus phi. Yes. Yes. Please, if you have any, I'm using very small screen, so if you have any questions, just use your mic.
Yes, Ibrahim, actually I have just some confusion, but I think it's about the terminology. So when we are referring, for example, to this perceptron or neuron or unit, but we are actually speaking about the feed-forward neural network. So this is what we refer to, the feed-forward.
Yes, we are not yet in feed-forward neural network. When it's a neural network, it's a network of neurons. So now we are working with a single neuron, in fact, so far, which is only this one. So this one, it's just a single neuron. We just are working, so far we are working with a single unit, but not with, but the next slide will be feed-forward neural network, right?
Okay.
Yeah, so
yeah. And you were also mentioning during the sessions, you were using two terminologies, the feed-forward neural network and the shallow neural network.
No, it's a shallow and deep. It's just the learning mode or how many hidden layers we have, right? All neural network have the same structure, but in deep learning, in shallow learning, we have a few number of hidden layers, and when it's deep learning, we have many layers of many layers. When it's many layers, it will be challenging for our optimizer to adjust the weights. So we will go into deep learning. Deep learning. So we call deep learning and shallow learning. And deep learning and shallow learning, it's just the number of hidden layers. So when the number of hidden layers, it's 1, 2, 3, 4, we can just call it's a shallow learning. But when it's 50 or 25 or 30, we can call it deep learning.
Okay, thank you very much for the clarification. Just I had this confusion and I needed to make sure that I'm using the right terminology. Thanks.
So now we can go to the feed-forward neural network because so multi-layer, feed-forward or just multi-layer neural networks, they call it multi-layer. So it will look like something like this one. So we have an input layer, we have a hidden layer or number of hidden layers, and then we have an output layer. So each unit here, it's a perceptron or adaptive linear unit. So far we have been using only one unit for solving problems. So we just have it's a single layer, right? It has some inputs and some outputs, and it's just one layer. And it's a single unit. We have only one unit, and we can use it for binary classification problems. We can use it also for multi-class classification, right? But it will be challenging for some problems. So if your data set is really complex, so in this case we can go into multi-layer neural network. And multi-layer neural network, just imagine this one. It's a perceptron. Okay, this one. So this one, it's just one perceptron, correct? So now we are just adding more perceptron together. So now we have many perceptrons connected together in layers, and we put it in layers, in fact, to make calculation much easy. Because when we put it in layer, we can just use matrix multiplications and stuff like this. So it will be very easy for us for calculation. We can use this. So in this case, we can add, and we can add just more layers. And when we add more layers, more perceptrons, we will have more parameters. It will be more complex to train, for example, but it will help us also to solve more complex problems. So it could be two layers, for example. I mean, we have input layer, we have one hidden layer, we have output layer. We can have also two hidden layers when we have two hidden layers. So it will be like this one. So when you increase the number of hidden layers, we can say that the model will be more deep, right? Because it will be challenging here also. It will be okay for adjusting the weights of the last hidden layer. I mean, when we train this model, for example, we go forward for calculating the output, and when we calculate the output, we need to calculate error signal, and we use the error signal here and go backward to adjust weights. Usually, it's easy to adjust the weights of, I mean, this layer, for example. It's okay, and maybe it's okay here also. But when you go deeply, it will be impossible because the gradient will reduce with time. I mean, the gradient, I mean, partial E by partial omega, it will reduce. This value will reduce a lot with a number of hidden layers, and at some point it will be very, very small to the degree that it will not help us to adjust the weights. And usually, when we train those models, we start by initializing all those weights with random numbers. So imagine that you have some weights here connecting the inputs to this layer. We have some weights here, and we are able to use the error signal here to adjust the weights of this layer, but not of this layer. So in this case, we will keep those numbers random values. When it's random, it will make it very challenging because those random values are multiplied. When those random numbers will stay fixed, I mean, the input to those layers, it will be the inputs multiplied by some numbers. So it will be a problem. It will make distortion to our data set, and it will be hard to train our model. So when you go deep, it means you are increasing the number of hidden layers. And when we increase the number of hidden layers, it will be really very challenging to adjust the weights, connecting those units with the inputs. So it will be very hard to adjust the weights, those weights, because of something we call it gradient, vanishing gradient. Vanishing gradient, it means the gradient function which we use to adjust those weights, it will vanish when you go towards the input. I mean, the value of those functions, those numbers will decrease a lot, right? And when it's very, very small, when it's close to zero, what will happen? We know the equation for adjusting the weights, omega equal omega plus delta omega. Delta omega will be very, very small, or even it will be zero. When it's zero, we will not adjust the weights. If we started with some random numbers, we will keep those random numbers all time. And if we have the inputs multiplied by random numbers, feeding them to the first layer, for example, first hidden layer, the problem, we will be dealing with random numbers, because a random number multiplied by a number, it will be a random number, correct? So instead of working with the data, we will be working with just a bunch of random numbers. So it's a problem. So when you go deeply, we will face this problem. Some of those weights will not be able to train the weights. If we started with some random values, we will keep those random values all time, because the gradient is vanished, because the gradient is very small. It's almost close to zero. So omega equal omega plus delta omega. Delta omega will be close to zero, which means we will not be able to adjust the weights. So this is the problem. We call it shallow learning when we have very few number of hidden layers. We call it shallow learning. But when you have many hidden layers, when you have 10, 20, 15, something like this, it will be really very challenging for, I mean, shallow learning techniques to train such kind of models, and we need to use deep learning approaches. How backpropagation works? I mean, we use the backpropagation, in fact, with a perceptron, right? At least for, I mean, regression model, for example. So we go forward first, and then when we go forward, we have some inputs here, we have some features. It could be x1, x2, and x3. Those inputs are multiplied by weights here, right, in the input layer. So the input layer, it's connected to the hidden layer with connections, and each connection has a weight value. So we have here weight. So for example, x1 is connected to this one by using omega 1, 1. This one it's omega 1, 2. This one it's omega 1, 3. This one it's omega 1, 4. This one it's omega 2, 1, omega 2, 2, omega 2, 3, omega 2, 4. So in fact, the weights of this layer, we can write it as a matrix. The dimension of this matrix will be 3 times 4, because we have here 3 features, 3 inputs, and in the first hidden layer, it has 4 neurons. So the dimension of omega here, it will be 3 times 4, correct? So this one, it's matrix. And we have the beauty of matrix multiplication, because if this one is a vector, this one, it's a vector. It's a 3 times 1, correct? It's column vector, right? So in fact, it's 1 times 3. When we multiply omega by x, we will get the values here directly in one step. So if you have this one defined as a matrix, right? So these weights here are defined as a matrix. So omega x, we will get numbers here. We will get the summations which we need here, right? Those summations, we will apply those summations to the activation function, because each unit here has an activation function. You can select rectified linear unit, you can select a Gaussian, you can select hard limb, correct? Any, because this one it's identical perceptron. So the summation of weights multiplied by inputs, we will get those numbers here in one step. You will apply those numbers. So those numbers here, it will be a vector. So the vector here, it will be 1 times 4. It will be a column vector, right? So just apply those numbers to the activation function. So you will get the output here in one step, right? So we will get a vector here of outputs. Those outputs also, it will be 1 times 4. We have here another weight here. So imagine also this hidden layer, we have here 4. So in this case, we can just call it V. The weights will here, I can call it V because I called this one omega. So V here, it will be 4 times 4. It's the same omega times output, which we got from here. We will get the summation here. Applying it to the activation function and repeat this process, for the number of hidden layers which you have. Finally, we will have some weights here. We can call it, for example, U, for example. So if the weights here, it's U, for example. So U times the output here, you will get the outputs here. So once you have the outputs here, you will subtract the outputs here from the actual output to calculate the error. And you will differentiate and you will go backward layer by layer to adjust those weights. If this one is deep, the gradient here, it will be very efficient here, in fact, because it's closer to the output. So the amount, the value of the gradient here, it will be very good, because this is the first hidden layer. We're adjusting now the weights of the first hidden layer, for example, or the output layer. We're adjusting the weights of the output layer. So because this one, it's closer to the output, the gradient here will be very, it's still raw value. We will use those values for adjusting those weights. And after that, we will go layer by layer to adjusting those weights. If this one is too deep, in fact, at some point, the gradient will be very, very small value, close to 0, and it will not help you to adjust the weights, right? So maybe the impact will be huge here, the impact will be little less here, the impact will be smaller, much smaller here, right? And you can do it, and you can plot the gradient. You can plot the gradient to see the amount, how much values we have. And from this one, you can understand the concept of vanishing gradient. Vanishing gradient, it means the value of the gradient will be very, very small, to the degree that delta omega will be equal almost 0. And when it's 0, we will not be able to adjust those weights. Please, if you have any questions, just use your mic. This I try to implement here multi-layer perceptron from sklearn, because it's very easy. I want to test it with. I can just give you a chance. If you can go to sklearn, for example, and try to implement MLP, multi-layer perceptron, and just as a hint, MLB, we call it MLB classifier. So you can import it from sklearn.neural network. Now we are working with neural network. Do you remember last time when we used a perceptron, for example? We can just import a perceptron here, right? But it's not .neural network, it's .linear model, right? So if we can go back to check, for example, for yes, logistic regression, for example, how can we import logistic regression? So we can import logistic regression from linear model, sklearn.linear model. You see here, this one, logistic regression or a perceptron. We import logistic regression or a perceptron from sklearn.linear model. Now we are working with MLP, And MLB, it's a neural network. It's not a perceptron. So in this case, we need to import it from sklearn.neural network. So you just need to import MLB classifier from sklearn.neural network. And the same as we need to know, we need to learn this pipeline of machine learning. When we are working with a model, we need to divide the data set into training and testing. So we need to use this function all time, train, test, split. This function is very important. So first, I mean the pipeline, it will be like this. I need to load my data. Now we can get my data. We need to upload the data. We need to maybe normalize the data. It's very important, or standardize my data. And after that, I need to select which model I will use. So based on your vision, based on your, when you display the data, you can just decide, okay, which model will fit my data. So for example, I said, okay, this data set is very complex, and I will use a multi-layer perceptron classifier. So in this case, I will import MLB classifier from sklearn.neural network. Now I trained my model. No, I want to train my model. To train your model and test it, you need to split your data into train test. So in this case, I will use this function, train test split. We import it from sklearn model selection. And after training your model, I want to evaluate the performance of my model. So in this case, we need to use confusion matrix. So from sklearn.metrics, we need to import confusion matrix. You need to import confusion matrix. Maybe you need to import recall, score, precision score, correct? So we need to import those functions to test the accuracy and the performance of your model. So now we are loading our data set and splitting it, right? And I use the stratify here. You remember? You see, I use the stratify. It's very important. You can use bin count to know how many classes are represented in each set, for example. The test size here, I used it 0.2. So 0.2 means 20% will be used for testing, which means 80% will be used for training. And this function, in fact, when you use train test split, this function will automatically shuffle your data set. So you don't need to shuffle it. Because what we're using was Iris dataset, and if you can remember, Iris dataset is 50. The first 50 classes for class 1, the second 50 for class 2, the last 50 it's for class 3. So it's not shuffled. So when you use train test to split, this one will automatically shuffle your dataset. It's very, very important to shuffle it. Otherwise, it will be divided. It will be biased, right? It will be biased. So this function, it has this nice advantage of shuffling your dataset automatically. After that, I got my MLB classifier. You see here. So I got MLB classifier. You need to select. You have lots of options. In fact, here the solver, which solver you will use. I just selected SGD. It's a stochastic gradient descent. This random state. This is the number of hidden layers. The size of the hidden layer. So I select one hidden layer with 5 units because I know that this model has 3 inputs, has 4 inputs, in fact. This Iris dataset has 4 inputs, but I don't know. Maybe I have been selecting only 2 features to display it in 2-dimensional space. No, I didn't. So I used the 4 inputs. We use the 4 inputs. So in this case, you need to select the hidden layer size. What is the size of your hidden layers? So in this case, I just use the one scalar here, 5. When it's only 5, for example, it means you have only one hidden layer, which has 5 neurons. This is the maximum number of iterations. You can specify. You can just Google it, for example, MLB classifier, sklearn. You will find all options here which you can change. There are some default. So by default, I can just remove all those, and I can just go by default. So, but here I just selecting those. Fitting your model. So I just MLB equal MLB classifier, MLB fit X train Y train. I need to test it for my test. So Y predict will be MLB predict, but in this case X test, right? It will be X test. You can calculate number of cases which are misclassified, this line. So some Y test not equal to Y predict. So this one will calculate the percentage of the number of classes which are misclassified. You can get the confusion matrix. I'm calculating the confusion matrix, right? For Y test and Y predict. and I'm plotting it. So I got it for the training and for testing. For the training, if you can see here, for class, for example, class 0, I have 40, and those 40 are classified as 40 from class 0 and classified as 0. We have 40 in each class, in fact, because it's 20%. So for this class, for example, class number 1, right? We have 40. 37 was classified as 1, and the 3 classified as 2. So we have some confusion here in three examples. So I have 3 examples from class 1 classified as 2. This number here. Do you see this number? And for class 2, 40 classified, correctly classified as 40. So we have only a problem in class 1, right? So we have only one problem here in class 1. And for the test data set, 10 0 classified as 0, 10 1 classified as 1, 10 2 classified. So the accuracy it's 100%. In fact, here it's if you want to check the accuracy in the training data set, we have only three cases which are wrongly classified. So it's 40 plus 37 plus 40 divided by the total number of cases, which is 40 times 3. If you want to get the accuracy here. So the accuracy also will be like 97% or something in the training, and in the testing it's 100%. But if you want to get better results, if you want to play with it, you need to change. Maybe you need to select a different solver, right? You need to increase the number of hidden layers. I can use 2 hidden layers, for example, if my data set is complex, correct? You can increase the number of units in each hidden layer. Maximum number of iterations, you can increase this number because it will be trained for this number and stop. And I used here stochastic gradient descent, and the stochastic gradient descent, it's the one which used for online learning. So if you got in the future any, I mean in SGD, for example, once we train the model, we don't need to keep the rest of the data set, right? So you can just delete your data set, you can just keep your model, and if you will get some new examples in the future, you can just retrain your model using those few examples. If you will be training your model using SGD, stochastic gradient descent. Yes, so this is for Iris. I want to leave you first to try to try to run this example first, and yeah. Any question, please? Yes. We can take a break now. We can take a break, and we can take, for example, 20 minutes, because I got a feedback that we are using very short breaks. And on those 20 minutes, please try to open this example and try to run it. Try to make some changes. So try to play with this number of hidden layers, for example. Try to select 2, 3 hidden layers. Try to increase those numbers, and try to see what kind of performance we can use. For example, we can get here. For example, I didn't normalize or standardized my features. You need to do this. Maybe you can get better results, right? So here, when I split my data set, I use the X and the Y as it is. So you know the range of X and Y, it's different. So you can normalize or standardize the X, for example, because we didn't do it here, right? And it's also one step which we need to do. Yes. Do you have any question, please? Any questions? You can just open your mic if you have any question. Now it's yes.
Can you explain the difference between a perceptron and a neuron? Because you are using these terms quite interchangeably, and it's difficult to understand what's the difference.
No,
a neuron and a perceptron.
No, perceptron it's a neuron with hard limb activation function, right? So it's a neuron with hard limb activation function. We call it a perceptron because they call it a perceptron. Maybe it's a historical name, but it's a neuron. And the neuron has those functions. We need to calculate summations, and after calculating the summation, we need to apply it to a cost function. If you will select a hard limb function, they call it perceptron, and they use this perceptron for binary classification problems. If it is, if you change the activation function into Gaussian activation function, we call it regression model, right? We call it. So we call it logistic regression. If you will change the activation function from hard limb into Gaussian, we call it logistic regression, right? So you will change the activation function into Gaussian function, but also you need to use this threshold function, because we need to make decisions, because the output from the regression function will be probability, and it will be number between 0 and 1. So we need to make decision, right? You can use it, and after that you can round it to the nearest integer. For example, you can just say this is my class, because if it is 0.7, it's logic that it will be 1, for example, right? If it is 8.5, it will be 1. If it is 0.49, it will be 0, correct? So we call it hypothesis. So so if you will change it to logistic regression, we will have this. It will be like this one. So this one, it's also we call it neuron, for example, with a logistic regression. So it will be the same. So we have the summation, and after the summation, we will apply the activation function. So we will have here a probability, right? And after that, I need to make decision. So I will apply this probability value to this unit step function. So the output from this unit step function will be my classes, class 1 and the class 0, for example. So it's, I mean, for names, it's neuron means 1 unit. When you add different, when you connect different neurons together and arrange it in layers, we call it neural network, right? But when it's 1 unit, it's a perceptron, or it's a logistic regression model, or it's linear adaptive unit, right? So in linear adaptive model, the activation function will be just linear function. I don't know if we have it here or not. So linear activation. So no, we don't have it. It was maybe a last previous one. So it's according to the activation function. So so a perceptron, it's a neuron with hard limb activation function. Logistic regression, it's a neuron with a Gaussian function. Linear adaptive unit, for example, it's a neuron with linear function, right? So but a perceptron or logistic regression or whatever, it's only 1 unit, 1 neuron, only one circle. But when we have many circles connected together, we can call it neural network.
All right, thank you.
Yeah. So now we can take a longer break, because it's not a break, it's a break plus you can get your coffee and you can relax a little bit, but also you can go to GitHub and open this file and try to change, I mean, the structure of feed-forward neural network or multi-layer perceptron, right? They call it even multi-layered perceptron. So at the end, a perceptron, it's a neuron. So they call it multi-layered perceptron, right? So it's multi-layer. Instead of using a single perceptron, we will put it in layers, and we will call it multi-layer perceptron. So so now you need to change and the plot also. So now we have the hidden layer size. I mean, we are lucky here, because when we are training it, it will get number of inputs from X-train and the number of classes from Y-train, right? So when we use this function, when we initialize the MLB here, we just need to specify basic things. Those basic things are the number of hidden layers, how many hidden layers, and the number of units in each hidden layer, number of iterations, optimizer, and so on. But we didn't specify here the number of inputs and number of outputs. How the model will understand the number of inputs and the number of outputs, it will understand it from the data set, right? So because we have here, when we train it, we have X-train and Y-train. So it will know how many column in the data set. Number of column will be the number of inputs, and Y-train, of course, the number of classes. So the number of classes here will be the number of outputs, right? So just to go to this, I mean this line, and try to change it, try to run it in different way, try to get better results or different results, to understand, because this one from sklearn, and it's very easy. And the next slide will be how can we train multi-layer perceptron from Keras, for example. It will be different in different way, but also it's a very, I mean, very good tool. So we will take a break now, and we will meet after 20 minutes. So we can just meet at, for example, 9. For example, is it okay? Or 9:45. So we will meet again at 9:45. And during this time, please take a break and try to go to GitHub and try to get those, I mean, those files, and try to play with the, I mean, with the functions, MLB classifier. Even you can try to use it for training MNIST dataset, for example. So we can meet at 9:40, for example, or 9:45, and during this time you can play also with MNIST dataset, which will be the next example. Yeah. So thank you very much. We will meet again after the break.